Yes, well, thank you everybody for being here, and thanks to Harm to sort of, I want to say tiring everybody out so no one will interrupt me, but that I don't mean to be dismissive, of course, for giving a great talk, and sort of a polar opposite to what I'm going to be talking about today, because I'm sort of in a very, very different field, in a very different place in the brain. I was thrilled when Peter first asked me to talk, and then immediately panicked, because what I do is loosely geometry, very loosely physics, and definitely not representation theory. But more seriously, I'm working statistical physics and lattice models in the plane mostly. And this is a thing that I think no one in this building has thought about much. So the way I sort of wanted, one of the reasons I chose to speak about this project is, first of all, there's sort of a good primer to a lot of the questions that I am interested in general. Also has a couple of pretty pictures and one or two proofs, which is simple enough to actually do in the slides as we go along. So I hope you guys will enjoy this. Also, I'm trusting at the very least Valerio to keep me honest in terms of questions. If anything is not clear, please stop me and please ask as many questions as you'd like. And this is joint work that I did with Nick Crawford at the Technion in Haifa, Sasha Glasman, who's currently in Vienna, and Ron Peled, who was my supervisor in Tel Aviv while I was a postdoc there. So without further ado, we're going to be talking about lattice models. So lattice models, the basic thing we have is the lattice. I'm sorry, this is actually, yes, is the lattice. And in this case, we're going to be working with hexagonal lattice, which I'm going to call by Blackboard H. This is an infinite graph, just repeating hexagon faces. Each vertex is of degree 3. And I'm going to use the calligraphic D to describe a finite subset of this graph. And the kind of models we're talking about are going to be loop models on this graph. But before I define them, I'm going to ask what is probably a very simple question, which is, what do uniform two colorings look like? So imagine that I go by the faces and just consider a uniform measure, that is, each one of the possibilities is going to be equally likely to each one of all possible two colorings of the face. When I say two colorings, I don't mean proper two colorings, because adjacent faces can be the same color. In fact, they must, because the faces don't make a bipartite graph. So things like this. We just sort of say, okay, I've got each of the faces red or blue with probability 1/2, which is in this case equivalent to the notion of a uniform coloring. In this case, I actually went down and had the computer at least flip coins to get this sample right. So a thing that's completely, if I take this coloring sigma, I can completely determine it by looking at the domain walls, which I'm going to call omega. So this set of loops in dark blue, where the set of edges in the loops are just the set of edges which separate red from blue faces. And we're going to call this set of all possible domain walls on a finite configuration L of D, the set of loop configurations. Now, you can think of these as domain walls, or you can think of these as just non-intersecting loops, or subgraphs where every vertex has degree 0 or 2. This is, by the way, where I need the fact that I'm on the hexagonal lattice and on a different lattice. Unfortunately, this is one of those things that it's very sensitive to microscopic details. You can define a lot of these objects in greater generality, but things get a bit messier. The thing on the hexagonal lattice is that two loops that are disjoint edgewise are also disjoint vertex-wise. So there's no problem of like two things meeting in a corner in squares, for example. So the loops are disjoint, it's perfectly fine. Now, if I take a uniform two coloring and consider the, sorry,
can I ask? Sorry, I missed what is uniform about the two coloring. So there's two colors, but what makes it uniform? Uniform in the sense of equally probable.
Exactly. Uniform in the sense that I'm going to pick one with weight 1 for each possible colorings. So in this case, there are exactly 2 to the number of faces coloring. Each one is equally likely.
All right.
Mm-hmm. So I was about to say, if I take a uniform 2 coloring, because the set of colorings is in bijection with the set of loop configurations, I can just very easily consider the set of uniform loop configurations. That is, pick one with probability equal for every one of them. Is that clear? Oh, hi, Chris. I don't know if it may work, but I'm hoping to. Anyway, so I'm now going to look, I can just as easily look at the set of the uniformly chosen loop configuration. Sorry, I got a bit distracted. And ask what it looks like. Now, this entire talk is going to be just talking about lattice loop models. And these models are basically going to be, when I say a model on loops, I mean some kind of a way to randomly sample from the set. Uniform means everyone is equally likely, but I can just as easily come up with weights, where I have a more complicated situation. Each configuration is more or less likely depending on certain properties of it, and ask what a typical sample of it looks like. We will do so in the future, but for now, let's stick to uniform choice. So there's a lot of things I can ask here. So let me just sort of be incredibly parochial and small and ask a very specific question. I want to distinguish between two things that these kind of typical loop configurations can have. On one hand, I'm going to have the property which I'm going to call short loops. Roughly, there aren't many loops. When there are, they're short. They're tiny. They don't cover much of the space. Most of my graph ends up being empty space. The other, shockingly, long loops. And long loops idea is that they cover a very large amount of space. They sort of, not maybe most edges, but a vast proportion of the faces lie on an edge. And you have these kind of nesting and these kind of interesting geometry in the background. And this is a paradigmatic sort of very cartoonish picture of what I mean when I say long loops. Of course, I am a mathematician and I would like things to be defined properly. So let me try to give you a sort of mathematically precise notion. The notion is nesting. On the left-hand side, I basically see no nesting at all, and I can imagine that as I sort of make my domain larger and larger, there might be small amounts of nesting, but relatively rare. On the right-hand side, the nesting is common, and in fact, infinite. And the idea here is that if I sort of make that domain larger and larger, and I look at a typical configuration, the number of loops that surround the typical face goes to infinity in long loops or stays down. So I'm going to say I have short loops if the probability that the number of loops is larger than any given k, and the infinite volume limit as d goes to h stays bounded. Or alternatively, if every face is surrounded by infinite many loops, I say I have long loops. Now, you might worry that there's a third option where some of them are infinite and some of them are finite. It's impossible. The loops are on a lattice. So if I have two faces and one is covered by infinitely many, so is every other one, because the number of loops that cover one face and not the other is bounded by their distance. So either none or all are covered by infinitely many. Okay, so I mean, it's a model, it's a probability measure. One of these things is going to happen, the other thing is not going to happen. And in fact, by sort of 3 steps and a jump of ergodic theory, you can say that each one of these things will happen with probability. So let me show you a picture. Here's a simulation of the uniformly chosen loop configurations. I think you guys will still look at this for about 1 second and say, yeah, this is long. And just to sort of, it's a bit hard to see with all this blue and gray. I picked out this one gray face and showed the red, the green, and the orange loops are the 3 loops that surround it. At this point, if you're anything like me, you might be thinking that I'm an idiot asking about nesting, because that is clearly not what's interesting about this picture, right? Sure, I have this one sort of small red loop, but this green loop is intricate. It's convoluted. It goes on itself. It's fractal in some sense. Now with the orange loop, who cares there are 3 of them? What's the geometry of them? That's where the interesting question is. And I 100% agree. It's harder. And it's sort of not where I'm going with it, but the sort of study of uniform loops is honestly, this is related to a model called the Bernoulli percolation, which is just given sort of the coloring model, the uniform colorings of the hexagonal lattice faces, about which I could probably teach a full semester long course. So it's only 50 minutes here. There's only so much I can do. Also, if I were a physicist, I would say, actually, the 2 sentences are equivalent, which is factually true and rigorously not at all established, at least not in the general case. But the sort of grand philosophical notion is that these kind of loop models in the plane can have 2 kinds of behaviors. The small loop behavior is one where basically the geometry completely degenerates. You don't see anything in the large scale. The loops are small and you sort of zoom out, you don't see anything. If you're in the large loop scale, not only do you have infinitely many loops and an arbitrarily large number of loops that go out, their geometry is fractal. And in fact, the big punchline here is conformal endurance. I'm not going to be able to talk about that in detail, but just sort of there is this, it's a situation where the kind of basically, as you zoom out or scale appropriately, you forget that you're in the lattice and you see something that sort of respects a far larger group of symmetries than you would expect from a lattice model, which really should only be rotated by like 120 degrees. Those are physicist notions in the sense that they are correct and I have no idea how to prove them. Or at least they're believed to be correct. In the case of the model I just described, it's actually rigorously known, but in general, it's not. The reason I focused on long loops now is because it's something we can prove, and we can prove it for many different models, many different weightings of the loop configuration, which is sort of where I'd like to go with this. Now, before I can move forward, I sort of have to deal with an annoying technicality, which is what happens. I kept talking about infinite graphs, and I kept talking about like the infinite hexagonal lattice, infinite number of loops, but I thought we were in finite sets. So how do you really resolve these two things? And the basic punchline is you can't take a uniform measure over an infinite set. That's not a well-defined option measure, right? Each element has probability 0. So if I want to say, okay, how do I actually take a uniform loop configuration in an infinite graph? The way I have to do it is indirect. What I do is I take a finite graph, Bn, a finite domain. I sample a loop configuration on it, and then I essentially take the limit as the boundary goes to infinity. And this process is called the thermodynamic limit. If anybody is concerned as to how this is done, this is formally done as a weak star limit of the measures. But if you don't like that, just imagine that you sort of look at a configuration with like a box of size 1, then 2, then 3, and just sort of look at all those things and sort of take an edge by edge subsequential limit. So you don't really have a limit, you might have many limits. In certain cases, it's unique. In certain cases, it's not. I'm basically going to hide a lot of those issues under the carpet. But if you have any question and that sort of things aren't clear, please ask. Luckily, we don't actually have to do this in the case of uniform coloring because we can cheat. Which is the thing I care about is the loop configuration, the domain walls. But I can remember that this came from uniform coloring. And the thing with uniform coloring is that I can sample uniform coloring, but just going face by face and saying, okay, you, blue or red, flip a coin. Great. You, blue or red, flip a coin. Completely independent. And that process you can easily do on an infinite graph. So you just take a uniform coloring and define the uniform chosen loop configuration, quote unquote, on an infinite graph by the domain walls of that process. And then you get something like this. Maybe this is my domain in dark colors, and you need to look on the outside. And the domain walls are now still going to be these loop configurations, except loop configurations might exit my domain. And in fact, they might not even be loops. It's perfectly kosher, according to this law, to have bi-infinite paths. So you can think of these as either loops that are so flat that you don't really see them closing, or as just an infinite volume, just the only restriction I really have is that the degrees must be 2 in each vertex, 2 or 0. Excuse me. So this is now a measure. Technically, if you want to ask, is it possible to have short loops? Yes. Is it possible to have long loops? Yes. But almost surely on this measure, I claim that I'm going to have only long loops. The kind of picture we saw before is really the reality. And believe it or not, I'm going to give you an incredibly dumb proof of this fact in 7 or 8 minutes. So this is what's called exotric, and it's a bit of mathematical folklore. And it starts with the following letter. I have a finite domain D, and I have a face which I call O. And I have some number L, some integer number L, which is just needs to make sure that it's big, but it's big enough, it's small enough that if I look at the ball of size L around the face O, I'm still in my domain. But if you think of the domain as O as sort of the center vertex and D is large enough, L can be arbitrarily large. Then if I pick a uniform loop configuration in this domain D, the probability that the face O is surrounded by a loop whose length is at least L, and by length I mean, let's say, outer parameter or outer radius, excuse me, the sort of the smallest ball that it fits in. is at least L, is at least 1/2. And the proof of this is completely combinatorial. And it's based on the idea as follows. Let me consider the finite, but possibly very large set of all configurations that don't have long loops surrounding it. So suppose that omega is one of those configurations. I have a bunch of loops. Maybe it looks like this. There's some part of it. Maybe there's a loop of size 2 that surrounds this face, but all the other loops don't surround the face that I care about. Maybe this one closes this way, maybe this one goes around, closes this way, but they don't surround it. Specifically, that means that if I look at sort of the outside of a ball of size of this green ball, for example, none of the loops that intersect this ball can cover the face. Basic combinatorial. I'm going to now consider this circuit gamma L, which is just a set of, it's not part of the loop configuration. It's just a bunch of edges that I draw in. Clearly, this circuit surrounds the face. Clearly, it's long. Its length is at least L by definition. But it's just a bunch of edges. It's not part of my loop configuration. I have a loop configuration omega and this thing. What I'm going to do is I'm going to produce a map from the set of loop configurations that don't have long loops to the set of configurations that do have long. And that map is nothing more than the XOR, if you'd like, addition modulo 2 of edges. I'm going to take all the edges which are either blue, that is in the original loop configuration, or orange on this loop, but not both. And a simple combinatorial fact will show us that this XOR operation takes a loop configuration to another loop configuration, maintains evenness of degree. And if I didn't have a long loop in the first one, I must have a long loop in the second. So in this case, if I just do the XOR in this picture, I get this purple loop, which goes all the way around and closes somewhere outside of my domain, but it's definitely pretty long. And it covers the gray face, which I call O. Now, the thing is, XOR is an involution. That is, if I take omega, XOR with a given loop, and then XOR again, I come back to where I am. And that means that the map from the set of all loops, of all configurations without a loop surrounding, to the set of all configurations that do have a loop surrounding, a long loop surrounding us, is an injection. And the combinatorial consequences is that the number of configurations with no loop is smaller than or equal to the number of configurations with loops. And that closes the thing, because in a uniform measure, the probability of landing in the set with long loops is its cardinality divided by the total cardinality. So if this set's larger, the probability is smaller. Nick Crawford first showed me this proof, basically guffawed. I guffawed, we all guffawed upon listening to this proof, because if you sort of take a standard percolation course, this is not how you prove these kind of facts. But it's sort of elegant in its simplicity, and it's pretty nice. It just tells you that regardless of where you look in this uniform loop configuration, you will have, with at least probability 1/2, a long loop surrounding the face. Now, this is not long loop. Remember, long loops I defined to be to make sure that if I have a single face, it's going to be covered by infinitely many loops. But it's not very difficult to prove that this implies long. So let me sort of see if I can give you that argument. And the idea here is that that lower bound 1/2 on the probability is uniform in pretty much everything. For any L, for any domain, I can always, if I pick the domain large enough, I'll find a long loop. And the result is the theorem, which is that if I want long loops in a uniformly chosen loop configuration, that happens with probability 1, with the annoying caveat, this is not a big deal, is that I have to have a priori ruled out infinite interpolation. If my loop configuration actually has a bi-infinite path, then the XOR might take the bi-infinite path to just another bi-infinite path. And it's not clear whether a bi-infinite path surrounds the loop or not. And it really screws you up if you have bi-infinite paths. So I'm always going to be working on conditioning that no bi-infinite path can exist. In many cases, you can rule that out a priori. In other cases, we don't know how to do it. Now, the idea is just keep on XORing. Right? What you do is you sort of take L1, L2, L3, this infinite sequence, and say, I'm just going to apply the XOR trick at every single level L. Each time I XOR, I have a uniformly large probability of creating a new loop surrounding the order. Now, you may think, why take L1, L2, L3? Just do it at 1, then 2, then 3, then 4, then 5. It's a good idea, but there's an issue here, which is that it's possible that if I XOR at L1 and then XOR again at L2, the second XOR will destroy the loop that I made the first time. And I sort of just have an alternating case of 1 loop, 0 loop, 1 loop, 0 loop, 1 loop, 0 loop. What you do instead is you sort of space these L0, these LIs out so that you know that you can't be certain, still a random object, that with good probability, let's say probability at least 3/4, when I XOR at the level L1 and then I XOR at the level L2, the second one doesn't destroy the first one. And then the third one doesn't destroy the second one. You sort of keep doing this. And it's a bit technical, but if you sort of set the things up properly and sort of do some very basic union bound style bounds, you can show that you have infinitely many opportunities to succeed. What do I mean by succeed? Either you create a new loop. The XOR trick works, and the new loop you surrounded didn't destroy any of the loops that you had before. So uniformly positive probability and infinitely many chances. It's very straightforward to prove that this implies that infinitely many of them succeed, and there's infinitely many loops that surround the fake loop. Now, it's a proof. I want to sort of highlight that it does have a few flaws. The first is that it's completely and utterly non-quantitative, in the sense that it tells me that I have long loops, but doesn't tell me that, like, okay, if I have a ball of size n, how many loops can I expect to find around the origin? By the way, the answer is of order log, but this argument doesn't tell you anything. It just tells you that that expected value must diverge. It also can't rule out by infinite paths, which is, as I mentioned, anyway. The positive part of it is that at least what's on this slide doesn't use uniformity anyway. This is sort of, you can think of this as a recipe, as sort of an algorithm. If I know that large loops exist with a uniformly positive probability, long loops follow immediately. So the XOR trick, in a way, is just a plug and play kind of result. It tells me on any loop model whatsoever. If I have a loop model where the probability of surrounding a face with an arbitrarily large loop is bounded below by 1/2 or any other number that's independent of everything else, long loops. And that's sort of going to be an important punchline, because there are going to be more than one model, because obviously we pretty much finished the question of long and short loops for uniform models, but we can ask this question about many, many different kind of probability measures, ways to sample loop configurations in a game. So let me tell you about probably the most well understood one, which is called the Loophole model.
Matan, can I ask a small question?
Of course.
Go back to the previous slide. If I take the XOR at one loop, compose with XOR at another loop, is this a finite order?
I'm sorry, can you repeat the question?
Yeah, so XOR, as you explained to us, at a given loop is an involution, right?
Yes.
And if I take the composition of two such things.
Oh, it's not, in general, it's not. It's a composition on the event that there are no loops that touch both that cross the annulus from size L1 to L2.
And sorry, if there are no such loops, then
if there are no such loops, then it becomes essentially a composition of independent involution. So yes.
Then it's a composition of
independent involution.
And so that means it's finite order. That means it's an involution itself. No,
it's an involution itself. Yes.
It's an involution itself. Okay.
Yes. So if you'd like, what you can say is you can say that assume that you consider the set that has only a finite number of loops surrounding the origin, and you can show that the cardinality of that set is smaller than it's smaller than 1 over k times the size that have a larger for any k. Therefore, it has probability 0 in the limit. In fact, I think that actually works regardless. I think two involutions, it's always going to be finite order. in that sense, I think it's always finite order. Any finite number of XORs is a finite order. The problem sort of becomes if you try to do infinitely many XORs, and we don't really do that. We do it an arbitrarily finite number can always get to prove that the probability that you have at most k is 0 for any k.
Okay.
Given that silence, I can assume that I only confused you in a greater way.
No, I think that's okay. That's helpful. Okay.
Okay. Basically, the probability is only 1/2, right? And it's possible that there is somehow the kind of enemy you may imagine is that with probability 1/2, you've got a lot of loops, and with probability 1/2, you've got none. Right? You don't really know how these interact with one another. What I'm doing here is essentially saying that with probability at least 1/4, for example, they're independent. That's the question of whether each one succeeds to give you a new loop is independent. Does that clarify?
Yes.
Okay. So that's the question of how it works for uniform models. So let me try to describe. There's obviously many ways to do it. Let me describe a non-uniform. And I'm just going to flash the definition on the screen here, but I guess let me just define it properly. The idea is as follows. I'm now going to be in a finite domain, and I want to give each of the loops a weight. And that weight is going to be x to the power of the number of edges in my loop configuration. Basically, what I'm saying is that I want to, if I imagine x to be smaller than 1, every edge of a loop costs me something. And the more edges you have, the more unlikely the configuration. Now, of course, I have to balance that versus the entropy of, let's say, how many different configurations of a property, and these two things will balance each other out to give me a different configuration in finite space. The probabilities will all be non-zero or 0 in a finite space, but be very different, at least a priori. And the way we do that formally is by giving the probability of any particular loop configuration omega, the weight x to omega. But of course, the probabilities have to sum up to 1, so I need to divide by z dx, which is just a normalizing thing, also called the partition. Now, this is the loop O1 model is also the domain walls of a coloring, right? I can just take a coloring and say, okay, instead of every time I see two faces of a different color, I'm going to give it a weight x. Equivalently, I can say anytime I see two faces of the same color, I give that edge a weight 1/x, just by symmetry, sort of counting things differently. This is probably, if you ever heard of any of these lattice models, this is the easy model, where you consider two colors, red and blue, and your interaction, each face talks to its neighboring faces. And if x is smaller than 1, that means you would like things to be of the same color. That's a ferromagnetic interaction. And if x is larger than 1, it's an anti-ferromagnetic using model, meaning that you'd like to sort of, each face encourages the opposite color. And these are in complete bijection. There's no difference between asking questions about one or the other. One thing that is unfortunate is you can't define the Ising model in infinite volume a priori either. So we're sort of stuck with taking these kind of thermodynamic limits. So I just take a box, sample the configuration in there according to this slightly convoluted rule, and then take the box to infinity. In this case, at least when x is smaller than or equal to 1, the limit exists and is unique. If x is larger than 1, we actually don't know. The answer is yes, the limit exists and it's unique, but we don't know how to prove it. It's almost shocking how difficult dealing with these limits are, especially in the case of the loop O1 model, because of the following incredibly aggravating fact. As x gets smaller, it makes a lot of sense that the loop configurations get smaller, right? If you say, I punish an edge of the vertex to be there, you imagine smaller x, fewer loops, right? That is 100% correct, but there is no known coupling, and I don't believe there's going to exist one, such that I can sort of have one huge probability space. That is, I slide x, I sort of slide x, slide x, slide x to the right, and all I do is just increase edges and have loops appear simultaneously. If I stop at any given x, I see the loop O1 model of x. There is none of these monotone coupling events. And that is weird, but then it makes sense when you think about it, because loops are sort of repel one another. If I tell you that there's a loop right here, then all of the edges that come out of it are automatically excluded from my loop model because the loops have to be non-intersecting. So this kind of local exclusion by entropic means, but just the fact that you're not allowed to use it, really makes life difficult in working with these loop models. You can usually work around it, but sometimes. Anyway, I now defined a new model, as is now the tradition. I'd like to show you a picture of the model.
Can I ask, Matan, why is it called O1? I mean, what does O stand for and what does the 1 stand for? Sorry.
The 1 is the parameter here. Notice there's a 1 here. I define the loop O2 and then the loop ON model shortly. Why is it O1? There is a relation, and this was initially posed as graphical representation in 2 dimensions of the spin ON model, which is actually comes from vectors in an n-dimensional sphere.
Mm-hmm.
I'm not going to discuss it exactly where it comes from, why it's O1, but you can think of the O1 as somehow the fact that you have 2 colors in this case, right? Blue and red. That's somehow the 0-dimensional sphere.
Mm-hmm. Okay.
And we're going to see the loop O2 model is related to integers, which is not quite the 1-dimensional sphere, but there is a sort of a way to get to make it into infinite covering of the 1-dimensional sphere. So there is a story about O model for the purposes of this talk. I promise that the 1s make sense. The O might be a bit arcane. I apologize. So I want to sample the loop O1 model for a couple of values. Here is the loop O1 model at x equals 0.6. And I'd like to argue, and I don't know if you'll agree with me, but I'd like to argue that this doesn't look very different from the uniform loop model that we saw before. It's long loops, it's convoluted. Nice. Here's the model at x equals 0.55. This is dramatically different, and in fact, this falls under the category of short loop. You really don't see, you see a lot of blank space, and you see these things don't really not really interact. You can probably guess by the picture that there's going to be something in the middle. In the middle, I've sampled it at x approximately equal to 1 over the square root. That parameter turns out to be the critical parameter for this model, because what we're seeing right here is a phase transition. As x decreases, you go from a long loop phase to a short loop phase with a critical phase in the middle, which also is roughly long loops, right? We have this one very long loop, but the geometry, the sort of fractal nature of the boundaries of these loops is different when x is larger than 1 over the square root of 3 to x being approximately 1. So the phase transition here, in fact, takes you from a phase which is long loops of one kind, a critical phase that's long loops of a second kind, and a supercritical phase, which is going to be essentially short loops. Whether it's super or subcritical depends on exactly your notation. I think of this as a supercritical phase, because if you sort of consider the colors, one of the colors dominates here. This is, I guess, blue dominating over red in the picture that I have here. You just consider the 2 color interfaces that is associated with the loop O1 model. So I included this for 2 reasons. First of all, it's pretty. Second of all, it tells you that these kind of loop models do have a short loop phase. It's not just like all of them are long loops always. There's at least a 1 parameter space, this parameter x, and if you push it small enough, we're going to get, a short loop phase if we just sort of discourage edges. Now, Valeria asked me why this is the loop O1 model. I now want to introduce a different model, which is going to be called the loop O2 model. And I'm going to do so in a bit of a weird way, because I'm going to ask the question about a different uniform set, which is a question about uniformly chosen Lipschitz. Now, this is not analysis. I'm still at the end in discrete world. So what I'm going to do is I'm going to take my finite domain D, and I'm going to assign an integer value to each one of the faces in such a way that 2 neighboring faces must have a difference of ±1 or 0. So formally, I have the set f of D, which is the set of all maps in the faces of D to the integers, such that neighboring faces can differ by ±1 or 0. And I'd like to ask, what does a uniformly chosen member of FB look like? because I like uniformly chosen things. And it's sort of an easy question. Now, the problem is that this question is nonsense. And if you sort of take about 30 to 40 seconds to think about it, you'll realize that if I take any particular map here, any H here, and just add 1 to each one of the faces, I get another member of FD, which is different. So obviously there's infinitely many things. If I just take the all zeros, the all ones, the all twos, there are infinitely many such things. So just to make sure that my questions are well defined, I'm going to consider the set of all faces of all possible height functions, as I call H, on the faces of D that are pinned to be 0 at the boundary. So essentially I take this domain, I say everything is 0 in the boundary, and my rule is that any neighboring guys can only be differ by at most 1. So this guy right here, for example, can be a 0, a +1, or a -1. That's the only one. But of course they interact. So here's a sample, and this is sort of hard to look. So I colored them by their heights. And at this point, I guess you're probably not going to be surprised, since I told you that I'm interested in loop configurations, is that it's very clear that any of these functions H generate a loop configuration by looking at their gradients. That is, I put an edge whenever the two faces disagree in terms of their height. This is fine, it's a map. But unlike before when we had 2 colors, this is very much not an injective map. Right? If I sort of look at this thing, there are going to be a bunch of different maps that actually map, a bunch of different height functions, excuse me, that map to the same domain walls of the. Right? Each one of these things corresponds to a gradient that can go up or down. So the way I like to think about it is that if you just give me these loops omega and ask what is the height of at this particular face, I can't answer that question. I don't have enough information for that. However, I can notice one thing, which is the height at this face. I can just take an arbitrary path from this height, from this point to this point. And by standard topological facts, I know that there's more clever topologists in the room than myself, but I hope you'll trust me that the number of groups you cross an odd number of times. So if I want to know what the height is here, I just need to figure out, okay, this loop right here, does it go up or down? This loop, does it go up or down? This loop, does it go up or down? And this loop, does it go up or down? This allows me, I can't determine the height, but I can determine its conditional distribution given omega. Specifically, if I want to know the height at the origin, given omega, the height is given by the sum of independent Bernoulli plus or minus 1 random variable, 1 for each of the loops that surround the face section. So in this case, it's the probability that this is 4 is exactly 1/2 to the 4th power. Probability that it's 2 is, well, you need 1/2 to the 4th power times the number of ways you can get to 2. So that's 3 ups, 1 down. So that's 4 choose 1 times 1/2 to the 1/2 power to the 4th power, etc. So you can actually write down the distribution very straightforwardly given the omega square. And there's sort of a more, I don't know, spicy way of writing that, which is instead of looking at distribution, if you look at the variance, the conditional variance of the height at the face given omega is exactly equal to the number of loops that surround. So the way I like to think about it is that the marginal, if I give you a height function sampled according to just any height function that's uniformly Lipschitz, and I look at the gradient loop, the number of loops that surround the face is exactly the variance structure of that height. And that statement had nothing to do with uniformity. If I sample a non-uniform function in my space FD, then its omegas are still going to give the variance structure of that probabilistic. So for me, not only is this just a really nice fact, because uniform Lipschitz functions are tough. They're just a really difficult thing to analyze. If you ever try to sort of play with them and try to get certain statements, it's not an easy thing to do. But loop configuration, also hard, but something that at least I personally knew how to do more about, so I was very excited about it. The other thing is that long loops now have a very nice concrete meaning. If I tell you that as this zero boundary condition goes to infinity, I have long loops, that means that the height at the origin, if you like, actually ends up diverging as the boundary conditions go to zero, go to infinity. So if I think of a typical height function, a typical surface given by this height function, where I restrict the gradient to be plus or minus 1, and I look at what happens at the origin, if I can prove long loops, then I can prove that basically that the fluctuations of that guy get arbitrarily long. Now, that's great, but in order to study the loop configuration, I need to know what are actually the loops. How do I actually sample the loops? And the idea is as follows. If I take a uniform map, I can do one thing, but I want to do it in greater generality, sort of following the loop O1 model, is I'm going to take a Lipschitz function, where again, I punish anytime I've got two faces that disagree, that pair gets a weight x, which I think of as a number smaller than 1, but I either punish or enhance. I prefer to think of x as smaller than 1. And that gives me a non-uniform, a measure on all of these Lipschitz functions. And if I follow what the marginal is, excuse me, in terms of the loop configuration omega, what's the probability of seeing omega? Well, I still have x to the omega, because again, the disagreement is there. But every loop can go up or down. So I can given a loop configuration, the number of different height functions that map to it are given by 2 to the number of loops, 1 for going up and 1 for going down. So my overall weight, my overall probability of getting a particular loop configuration by this operation is x to the omega times 2 to the number of loops. And this is why it's called the O2 model, because this number here, parameter here, is going to be 2. And in general, as you'll see in a second, I'm going to define the loop ON model, where this 2 is just an arbitrary parameter. It's tradition, I must do it one last time. What do these loop models look like? Here is uniform loops. The loops given by uniform Lipschitz functions, I'm sorry. This is the loop O2 model at x equals 1. It's sort of hard to see. Here is just, I just colored the 3 largest loops, so you can see they are convoluted, differently convoluted than the pictures we saw before, but they are convoluted and they do sort of fit in my understanding of what large loops are. Here is the model at x equals 0.64. I picked this number because it's the same number that I used for x equals 1, for n equals 1, excuse me. And this one actually ends up being super critical in the sense that these loops are very small. Normally, I would actually give you a third picture for the critical parameter, which is 1 over the square root of 2. But in this case, it's qualitatively no different from x equals 1. I basically ran the simulation and got a very similar looking picture. So I didn't really bother with pointing out there. And again, I recall that this kind of fractal behavior really actually shows you that these height functions, these associated height functions, are believed to delocalize, go to infinity if x is equal to 1, and localize, stay bounded, regardless of how far you put the boundary condition, if x is sufficiently small, 0.64. Okay, I've been at this for about 45 minutes and I still haven't defined the model. So let me the formal definition of the Loophole model is as follows. I now have 2 parameters, x and n, and I just say, okay, the probability of a loop configuration in finite domain, n to the number of loops, x to the number of edges. And again, if n equals 1, this term drops out and we get back to just the Loophole model. If n equals 2, I get this sort of push forward of the uniform Lipschitz functions. And it turns out there's one more case that actually has a very meaningful example, which is n equals 0. N equals 0, you think, okay, if you're not allowed to have any loops whatsoever. But if you sort of futz with boundary conditions, then I'm not going to bother with boring you with all the technical definitions of how to do it. You can make it so that you basically force exactly one path to start from one point in the boundary to another. And what you get by sort of setting n to 0 there is a model that's supported on self-avoiding paths on the hexagonal ladder. And it turns out that if x is small enough, you're basically just going to see a straight line. If x is large, you're going to see a space-filling curve. And if x is just right, you will see something weird and convoluted. And that correct constant is what's called the connective constant, which is a combinatorial statement on how many paths of length and self-avoiding paths of length n are there in segment with segment line. So the loop ON model sort of is this super model. I just heard myself say that. It's sure, I'm going with it. The super model, which includes the easing model, the uniform Lipschitz model, the self-avoiding walk, and a whole bunch of continuing things in the middle. And it doesn't really make sense that this would be a good thing to look at, except it does. It just works out in certain ways that even in non-integer values of n, certain miracles occur. And these miracles sort of led Nienhuis in the 1980s, who's a physicist, to conjecture a phase diagram for what this loop ON model should look like. I emphasize that everything I'm going to show you is conjectured, not rigorous, but it's a pretty and really tantalizing picture. So here it is. I have this curve right here. Along this curve right here is xc is 1 over the square root of 2 plus the square root of 2 minus n, because obviously, why would you pick anything else? There's a very good reason for this choice. It ends up being the solution to a particular trigonometric equation. And what Nienhuis claimed was that if x was smaller than this parameter and n was smaller than 2, then this entire region has not only small loops, but exponential decay. That is, the probability that the largest loop around you is larger than k is exponentially vanishing in k. What is more surprising is that this actually works regardless of the value of x if n is strictly larger than 2. So the loop O 2 plus epsilon model does not have long loops ever, at least according to Nienhuis's conjecture. On the right-hand side, not only does he imply long loops, he actually conjectures conformal invariance. Now, I mentioned this very briefly a little bit ago, but what conformal invariance tells you, the easiest way to think about it is not to think of thermodynamic limits, but scaling limits. So the idea is as follows. Take your favorite element, your favorite finite domain in R2. It's a continuous thing with very smooth boundaries. And on that, I want you to draw a tiny little hexagon. You sort of tile it with tiny little hexagons that might not fit perfectly at the boundary, but sort of approximate the boundary nice enough, and fill it with a little hexagon. And on those hexagons, sample the loop ON model at one of these points. So let's say n equals 0.8, x equals 1.2. So this point right here. Instead of taking the domain to infinity, take the mesh size of those hexagons to 0. If you believe in the long loop picture, which is proven in certain parts, but not the one I mentioned, then you imagine that sort of you get infinitely many infinitely convoluted loop structures around every point. And if you believe those pictures, those things are actually fractal. And you get these very convoluted kind of things. And if you sort of find the right topology to do this, you believe that this converges to a random fractal object. That random fractal object is going to be invariant with respect to every single Mobius transformation. So rotations, scalings, and inversions. Everything I'm saying is not only non-obvious, but almost, it strains incredulity in many ways, because the hexagons really respect only rotations up to 120 degrees. How on earth is it true these are going to respect rotations up to like 10 degrees, which completely skew the lattice? It turns out that conformally invariant models forget the lattice. They sort of forget the fact that they're lattice models. When you take these limits, they really sort of explore space in very, very constrained, but also rich, like geometrically rich ways. The work of Schramm in the early 2000s, which was then developed on by, I guess, Smirnov and then Werner and many, many others, actually characterized the one-parameter family of all such possible random distributions. They were called Schramm-Leibniz evolutions, and then they sort of expanded to things called CLEs, conformal loop ensembles. And there's a parameter kappa which describes these. I'm going to say something which I'm probably going to regret, but this is somehow related to the notion of central charge in terms of conformal field theories. I say that just because I know that it's a thing that people who care about deeply. I am far from an expert on it, so I will do my best to answer any questions if you have them. But there is this kind of, all along this line and along this yellow region, there is conjectured values of kappa for the associated conformal objects that we get. The weird thing is that along the line and just to the right of the line have different values of kappa which depend on it. So you have one value along the line and a value here, except that n equals 2 when there's only one value. That value is c equals 1, by the way. Kappa equals 4 and c equals 1. That's the one I already know. Now, unfortunately, at least from the perspective of a mathematician like myself, this is science fiction. Exponential decay has been established in certain places. Conformal invariance has been established in exactly 3 places. There are 3 known models that are conformally invariant, 2 of which are on this picture right here. So let me take a second and sort of confuse you even more by telling you, I believe, complete picture of all rigorous results on the Loophole. So in this weird little facial kind of, I don't know what it is, this cliff face, this purple cliff face, we know how to establish exponential. On the line n equals 1, this is totally classical. This is stuff that was known all the way back in the 30s and 40s through the work of Harel and then Onseger, excuse me. It was not in the context of the Loophole 1 model, it was the context of the Ising model, but they're easily converted from that. The rest of these kind of extensions are actually much newer. I think 2018, the work of Levente. So this is nice because it actually tells you exponential decay happens in certain areas. On the Ising model to the right, the result, sort of the state-of-the-art result is what's called macroscopic loops. Now, the way I think about macroscopic loops, I'm not going to define it formally because it's a bit of a digression to do it properly, is that it's a lot stronger than long loops. Not only does it tell you that you have infinitely many loops around them, it essentially tells you that much more interesting question of fractality. It tells you that these loops are convoluted, that if you sort of, in any sort of sizable limit, their Hausdorff dimension would be larger than 1. Strictly smaller than 2 and strictly larger than 1. It's these kind of estimates. Making it formal is a bit of a pain, but it basically tells you that subsequential limits of scaling limits exist, fractality exists. It's some kind of really nice random fractal picture. And that holds for any x between that's smaller than or equal to 1 all the way to the critical point when n equals 1 and along the critical line. And this second story, the story of what happens when xc is exactly equal to this number, is really deeply a story about exact solvability. The buzzword around here is the Smirnov parafermion observable. If that doesn't mean anything to you, don't worry about it. But it basically uses some very, very exact relations on the hexagonal lattice to note that if you sort of weight n and x just right to cancel each other out, which is how Nienhouse conjectured this line in the first place, you can sort of show lower bounds on the size of loops that arise basically by magic. And the final macroscopic loop result is actually right here at x equals 1, n equals 2, corresponding to these uniform Lipschitz height functions, which is a totally different thing, just a brilliant piece of work by Sasha Glasman and Ioan Manolescu, which somehow doesn't fit the paradigm of what I'm talking about, but it's too good of a story not to tell. So I wanted to make sure I mentioned. Finally, the crown jewels of these kind of loop questions is conformal invariance. And for x equals 1, n equals 1, this was the Stas-Smirnov work in 2010, and then 9. And then for critical easing, this was Chaukak, Smirnov, and Werner. These are, if I said what the results before were exact solvability, this is exact solvability on cocaine. This is incredibly fragile and careful work about what happened at these 2 points where the loops don't matter, so certain things become even easier. And I can't even begin to say how like wowing the results are in terms of just being able to understand the fine structure of these random objects in order to prove conformal invariance. The reason I mentioned it is not only they're impressive, but just how fragile all of these results are. They really only work on certain lines. So at these sort of either uniform points, critical points, or Ising point, which is magical by itself. The one final thing I want to say is that there is a very important tool, which are the so-called dichotomy results, which holds an entire region, which doesn't tell you whether it's short loops or long loops, but what it does tell you is long loops implies macroscopic loops, and short loops implies exponential loops. So basically, this is sort of the physicist's dream region in a way. It's not quite. It would be the dream region if long loops implied conformal invariance. We're nowhere near there, but it's pretty good. It sort of says that thing I said in the beginning, which is infinitely many loops, is it related to fractal behavior? Yes. Short loops, is it related to exponential decay? Yes. So this picture right here is essentially the state of the art of the Loophole model. I think every result but my own is actually on this picture. That's known at least circa 3 months ago when I last did a literature review on the material. I doubt if anything else has been discovered since, but this is not much if you sort of compare it to the much more grandiose picture we saw from Nienhaus's conjectured thing. And what we did was sort of, our contribution to all of this story was that we actually managed to sort of fill in an area around this. So again, I've been talking for almost an hour and I still didn't state the result that I'd like to prove to you. So this is, as I said, joint work with Nick Crawford, Sasha Glaserman, and Untitled, which essentially tells you that if you look at a region around the point 1,1, we can prove long loops in an entire quarter neighborhood around it. So visually, I have this little square here around the point 1,1, and everywhere in that region, I can prove long loops for any translation invariant thermodynamic limit. The details shouldn't matter in the context of this talk, but we basically are able to establish a long loop result and therefore macroscopic loop results where it lines up with the dichotomy regime for that entire region. Now, the thing that I sort of want to emphasize about this result is that it's not an exact solvability result by any stretch of the imagination. We use uniformity, but not in the sort of standard way. We don't need any exact solvability to make it. This is sort of the first result that actually is able to analyze these things without using miracles that happen at certain values of x and n, or certain symmetries that come from n equals 1, which make your life so much easier. And the other thing that's sort of spectacular about this, if you ask me, and I don't mean to toot my own horn, is just how silly it is. Because what we're going to do is we're just going to take that XOR argument that I mentioned 40 minutes ago, which only worked for uniform loops, right? It was a counting argument, it was combinatorial, and somehow adapt it to non-uniform measures. Now, Peter, how much longer do I have? I don't want to take too long.
Well, I mean, technically about 4 minutes something.
Okay.
I mean,
so I'm going to do this. I'm going to do a quick rush job and skip all of the details. I just want to give you a very quick idea as to how these things are going forward, because the idea is also very silly. It's to take non-uniform measures and find uniform measures in them. And excuse me if this goes a bit fast, but I want to just do it very fast, is I'm going to take the case n larger than 1 and x equals to 1, which is just a subcase of the general one, but it's simple. And what I'm going to do is I'm going to do what's called a defect representation of my loop O(n). And it's based on a very sophisticated formula. I take the probability of finding a loop, which is in a finite domain, the normalizing constant times n to the number of loops, and I write it in the following incredibly sophisticated way. N is equal to n minus 1 plus 1. I'll let you guys have a second to deal with that brilliant, brilliant trick. And when n is larger than 1, all jokes aside, the point is that I now have a positive number here plus 1. And what I'm going to do is I'm just going to write the binomial. If I have n minus 1 plus 1 to the power of the number of loops, that means that I can sort of take each loop and say, assign to it, you're 1, you're 1, you're n minus 1, you're 1, you're 1, you're 1, you're n minus 1, like that, and sum over all the possible summation, all possible assignments to get n minus 1 plus 1 to the number of loops. Geometrically, what that is I take a loop configuration omega, and I two color it, red or blue. And I say blue every time I assign n minus 1, and I assign the weight 1 every time I see that. I see, yeah, I see one. I assign red every time I assign one. So when I do that kind of binomial theorem trick, I can rewrite that weight as just, I go through all possible assignments of red and blue. The blue ones get weight n-1, the red ones get weight 1. Algebraically, a very simple fact. And what we're going to do next is we're going to do the standard trick that probabilists love to do, which is play with conditional probability. Because if I give you omega, if I give you all the loops and I ask you, okay, given omega, what's the distribution of red versus blue? Easy, literally go to a loop, flip a coin. n-1 over n, blue. 1 over n-1, red. Go on and continue. The question I'd like to ask is, okay, suppose I don't tell you all the loops. I just tell you the blue loops. Given that information, what's the distribution of the red loops that are still left over? If I gave you omega, if I tell you all the loops, it's just the loops that are left over. If I didn't tell you what they are, however, just looking at this formula and noticing that the WR doesn't appear anywhere, it turns out that the red loops are uniformly distributed among all loops that miss the blue loops. So if I say, okay, here is the set of red loops, of blue loops, excuse me. The red loops I can just complete to get a true sample of omega by I'm going to pick uniform loops on the complement and then forget the colors. And what I get is my initial loop ON measure. Okay, who cares? Well, I care very deeply because uniform distributed configurations are the things I know to do the XOR trick. So if I can find this green loop gamma, which avoids my blue loops, then XOR with this green loop is an involution on the set of all possible red. And if I pick that green loop to be large, I know that the XOR trick, if I actually do the XORing right, I can find large loops. So the way the argument works is as follows. If I can find these kind of green loops that avoid these small defect loops in blue, then I can get that kind of estimate like I had in the very beginning of the talk. The probability of having long loops around my vertex is uniformly large. And then I can just long loops followed by the algorithm we gave. So I'm just going to end on a pictorial explanation of how the proof works. This is an actual sample of the loop at n1.1. The colors are just there to make the loops easier to look at. I take these loops and I recolor them with two colors, red or blue. Red with probability 10 over 11, because n is equal to 1.1. Blue with probability 1 over 11. And here is a particular version. Now, it's a lot of loops, but I don't know if any of them actually surround. But I know that if I do the XOR trick, I want to take sort of, let's say, this boundary loop and do XOR with it. But I'm not allowed to, because I'm only allowed to XOR with loops that avoid all the blue. So what I do is I just sort of like, okay, I crawl along the boundary and move around, just to make sure that I could find a large enough green loop that avoids the blue loops, do the XOR operation on it, and then I get these very large loops. And to take a bunch of slides that just sort of explain how to do this, it turns out that at least if n is close enough to 1, that is, if n is between 1 and 1 plus delta, we can show that we can find these kind of green loops through the XOR operation. We can find infinitely many of these things with probability 1 on any kind of graph. And weirdly enough, that ends up being a question of isoperimetry of all things. But I guess I've already talked long enough, so I'm just going to skip these kind of technical slides for a second. Sorry about that. And just say thank you very much for listening.